Hello and welcome to SAGIS training video number 12, the last video in this series of SAGIS training videos. Congratulations on making it this far, and I hope you enjoyed learning about SAGIS-SIMCAT. This last video is a little bit different than the previous ones. Rather than learning how to drive the SAGIS add-in or learning about the different tools in the SAGIS-SIMCAT system, what we're going to do is take a deep dive on how SIMCAT, the river water quality model that we use, actually works. Take a look at the internals, the assumptions, the maths, and the equations behind it. This information is going to be key in order to use the results for decision making. Hope you enjoy it. Let's begin.
In this SAGIS training video, we're going to make use of the SIMCAT manual written by SIMCAT's creator and developer, Tony Warren. At the moment of recording this video, the official version of SIMCAT used within SAGIS is 15.7, although version 16.2 is in development and soon should be released. The SIMCAT manual contains a series of appendix, in particular Appendix 1, 2, 3, and 4, that explain how SIMCAT works, that is, the underlying math behind SIMCAT. This video tutorial will make use of the material explained in this appendix. We'll talk a lot especially about Appendix 2, river chemistry, decay, dissolved oxygen, simulation, time of travel, and temperature. Of course, these are very complex topics, and all of them could use with several books and PhD theses to be explained. In this video, we'll try to strike a balance and go into as much detail as necessary in order to understand how the general process is working. But in order to go through all of the topics, we'll have to scratch the surface in some of them, not being able to go in as much detail as we would have liked. Sometimes we might expand on what the manual explains if we have learned things that have turned out to be important when interpreting the results that are not included in the manual, and sometimes we'll have to provide a more general explanation of concepts that are explained more in depth in the manual. This manual will be an excellent source of material after you've seen the video in order to expand your knowledge about how SIMCAT works. A very important concept in SIMCAT is that of the mixing zone. Let's imagine that we got a river represented by a simple blue rectangle. In the middle of the river, we have a discharge, represented in this case by a black triangle, and everything after the discharge is what we called the downstream of the river. Now, between the upstream and the downstream, we have the mixing zone. Unlike a real mixing zone, which depends mainly on the width of the river and can range from a few meters to kilometers, the mixing zone in SIMCAT is instantaneous. It's exactly at the point of discharge. And in SIMCAT, the mixing zone is represented by a single equation, which is this one. Let's take a look at each element of the equation. The upstream is represented by the first item, which is capital F times capital C, river flow times river concentration for a particular determinant. The discharge is represented in a very similar manner by the second item of the equation. Discharge flow times discharge concentration, represented by lowercase letters. And then the downstream equals the rest of the equation. River flow plus discharge flow multiplied by the downstream concentration, represented as a T. In SIMCAT, we often see a different version of this equation, which is the same equation but solving for downstream concentration. And this is explained in the SIMCAT manual in item 206, mixing a single discharge with a river, where the expression appears solving for downstream concentration. This is also called the mass balance equation, where we're basically saying that the load coming from upstream plus the load coming from a discharge needs to be equal to the load downstream. Another very important concept in SIMCAT is correlation. What do we mean when we say that two variables are correlated? Correlation is a measure of how two variables are related to each other. So for example, imagine we got two sets of data, x and y. We say that these two variables are correlated if they move together in the same direction. We talk about a negative correlation if they move in opposite directions. So an increase in x causes a decrease in y. And then finally, we talk about no correlation when they don't seem to affect each other at all. When we discuss correlation in SIMCAT, we're generally interested in correlations between variables that appear in the mass balance. So river flow, river concentration, discharge flow, and discharge concentration. We also refer to concentration as quality. So for example, when we talk about river quality, we mean the concentration of a particular determinant in the river. Let's take a look at the chart on the left. This chart is showing the river flow and discharge flow correlation, which in this case is 0.6. It's a moderate to strong correlation that indicates that at higher river flows, we generally observed higher discharge flows, but not always. On the chart of the right, we see the correlation between river flow and river quality or concentration. At higher river flows, what we see is increased dilution capacity that results into lower concentrations. However, this is not always the case. There's other processes. For example, higher river flow might indicate that it is raining and therefore there is runoff for specific chemicals. This is a particularly weak correlation of minus 0.2. Also very important to notice at the top and right sides of its chart, we have the distribution of the variables that are being analyzed. SIMCAT usually represents different distributions using the statistical moments of the observed data for those variables. That is the mean and the standard deviation for most variables apart from river flow, for which we generally use the mean and the Q95, which is what we call the fifth percentile of the river flow distribution. That is the value that it's being surpassed 95% of the time. Monte Carlo is the key process that brings everything that we have seen so far together. It is the main methodology underpinning SIMCAT and also its related river quality planning software tool that I'm showing on the right-hand side of the stream. Now, how does Monte Carlo work? Let's recap. On the one hand side, we've got variables that appear in the mixing model, the mass balance equation. So this is river flow, river quality, discharge flow, and discharge quality. Now, those variables can be represented as distributions via their statistical moments, mean, standard deviation, and percentiles, assuming that they follow a certain distribution, normal or generally the log normal distribution. We use the Monte Carlo process to sample random data from those distributions in a very specific manner that takes into account the correlations between those variables. This will give us, and here we go to the graph to my right, a series of assumed distributions, in this case A, B, and C. Now, the Monte Carlo approach will take a random sample many times for each one of those distributions, pass them to the mass balance equation for a result, in this case the downstream concentration and downstream river flow, and it will, by repetition, shape the distribution that we have downstream of the discharge. Another very important process is decay. Decay is the approach that SIMCAT takes to represent the natural purification processes that reduce in-stream chemical concentrations in rivers. In SIMCAT, this takes the form of a very simple equation. Let's imagine we have got a graph with the load on the y-axis and time on the x-axis. As you can see, the load will disappear over time, as represented by this equation on the screen, a differential equation indicating that the variation in load over time depends on a constant, the initial concentration or load, and the time that it has passed. Now this equation has a very simple and well-known in the scientific world analytical solution, which means that we can know what the load is going to be after a specific period of time, as long as we know what the initial load is, the constant, and the time. Now this is how we solve the equation for a constant of 1. But now let's take a look at the values of different versions, different values of lambda. As you can see, as the value becomes lower, less load is degraded. And if the value is 0, then no load will be degraded at all. Our next concept is travel time. As we've just seen with decay, we need to know the time that it takes for the water to travel between 2 points in the river. And this is because the time will determine how much load has been decayed between those 2 points. Now let's see how this is calculated in SIMCAT. Firstly, we have velocity equals distance over time. Now, if we are interested in time, we can simply solve for time. So time equals distance over velocity. In SIMCAT units, this means that days equal the reach length between those 2 points divided by the river speed. Now, velocity or river speed is kilometers per day. So the units in the main equation at the top say that days equals kilometer divided by kilometers per day. So the units for days or time are of course day. Now imagine we've got a chart with the velocity on the y-axis and the flow on the x-axis. What is the river velocity? River velocity is determined by this equation. This equation has 3 parameters. Alpha, the velocity when the river flow is at the mean value, the ratio between the flow of each particular Monte Carlo shot, which is processed independently alongside the model, and the mean river flow, and beta, which is simply a constant that will affect the shape of the function. Typical values or default values for alpha and beta are 30 kilometers per day and 0.5, although these default values are generally not used in models. If we have a mean river flow, for example, of 50 cubic meters per day, the equation will look as it does in the screen. As you can see, when the flow is 50, the velocity equals the mean velocity 30. So with different betas, we would get different shapes. As you can see, with a beta of 0, the flow would be constant, whereas with smaller values of beta, we get a sharper increase that smoothes out the higher the value of beta. When beta approaches 1, the increase in flow velocity represents a straight line. Biological oxygen demand, BOD, and dissolved oxygen, DO, are the only 2 determinants in SIMCAT that are modeled with another set of equations on top of the previous equation that we have seen for decay. Let's take a look at what these equations look like. We're going to start with BOD. For BOD, the decay constant, lambda, or in this case k, is recalculated at every point in the river. So the new constant depends on the old constant, a series of values, and the concentration of BOD at that particular point. That is, the decay is proportional to the concentration of BOD, which makes it the only determinant in SIMCAT that is not linear. Now let's take a look at dissolved oxygen. Dissolved oxygen needs more equations. The first one is the DO saturation, the concentration of saturation for dissolved oxygen in the river, which might look very complex, but actually only depends on temperature, which is in 3 items, as you can see on the screen. The next equation is the deficit equation. So the saturation that we already have minus the dissolved oxygen concentration at that particular point equal the deficit. And what SIMCAT calculates is the variation of deficit over time, which is represented by a constant K. In this case, this is the same K that we've seen in the first equation. So it's the decay of BOD, the concentration not of oxygen, but also of BOD, because BOD represents the demand of oxygen in the system. And of course, we need to subtract from the deficit the reaeration, represented by that reaeration constant, as well as the deficit, because the reaeration is proportional to the deficit of oxygen in the system. The last set of equations that we're going to study today, I promise, belong to temperature. So let's take a look at how temperature is modeled in SIMCAT. The main thing that we need to understand is that temperature is adjusted within each single Monte Carlo shot, and it depends on flow, is correlated to the flow value. So the value of the temperature for a particular shot will depend on the ratio between the flow of that particular Monte Carlo shot and the mean flow in the river, and is adjusted by the equation on top. This adjusted temperature will have an effect on the decay values used for different determinants. For example, in the screen we got the equation for BOD, the equation for ammonia, and the equation for the reaeration. They are different, but they follow the same structure. Initially, they depend on the constant at 20 degrees, followed by a value that will affect the shape of that function, and then finally the difference between the actual temperature for that shot minus the temperature of the constant at 20 degrees. Another very important functionality that SIMCAT provides is the tracking of both point and diffuse sources. Now, we have already learned how to use some of these outputs in previous videos, in particular video 4, visualization, and the create output tables functionality. Now, I'm going to go back to this functionality, but this time we're going to go into more detail about where the data is coming from and how SIMCAT has generated this information. If you remember, when we click on Create Output Tables, we can create information for seaway streaming works, outputs, diffuse sectors, and inputs. For this video tutorial, I'll be using the first three: seaway streaming works, outputs, and diffuse sectors. Now, let's take a look, for example, at the point sources. This is tracking information. In contributing seaway streaming works, we have, for each catchment, water body, the relative percentage of contribution coming from each point source. We have already gone into detail on this table, so I won't go into in as much detail here, but just as a reminder, this is tracking information. Another table is contributing output loads. Similar to contributing outputs, which contains concentrations, this table contains loads. Now, this is not tracking information, this is routing. This is sector apportionment. Why is that the case? Because the information contained here is split by sectors, but is not in context of the other sources. So for example, what we can see here is that for water body 9 and the second determinant, orthophosphate, as a reminder, we'll have a load, and this load, for example, let's say for livestock 0.56, this is the load that can be found at this particular water body GV9 boundary point in the map. Plot outputs will show you concentration relative to, for example, the mean concentration and the sector apportionment per concentration. And now in this table, you can also learn about the loads per sectors. But what if what we want to know is the tracking information? So for a particular water body, what is the apportionment for a particular sector and determinant of each water body upstream? Now this information is contained in the tables named contributing followed by the sector name. So for example, we're talking about livestock for GB water body 9 for orthophosphate. If I go to test contributing livestock and I navigate to orthophosphate and to GB water body 9, I can see the load and the percentage contribution from specific water bodies upstream. In this case, this is a lake. This information, all of the information that we've seen in the tables, comes from two types of files, the D files and the P files. In particular, the D files are the ones used by SAGIS to bring all of this information into tables. Now let's take a look. As a reminder, I think we've already taken a look at the D files in previous videos. This is what the file looks like. It's not a table. It's information that needs to be processed row by row with an understanding of the information contained in each row. I've got this open here, already pre-filtered to show the rows that contain the information that we were looking at in the tables. So this is the D file. In column D, I've filtered by mean loads from livestock farming. And in column B, I've filtered by this particular feature. So column D contains many different types of information that SIMCAT has created. And column B, in this case, after filtering column D, will contain one row per feature or plotting point or output. One row per point in the map where SIMCAT has generated an output. And now we can see here 0.5 and then with some rounding 6. So this is mean loads from livestock farming, the mean load at this particular point in the map that can be found in the contributing output loads table. For this particular determinant, as indicated by the name of the file, D2, so that's the second determinant, orthophosphate, this particular sector, and this particular water body. Now, what about test contributing livestock? So this information, if we go back to the D files, is contained in the rows indicating annual mean load from this subcatchment from, where column E indicates the sector and column B indicates the water body that we want information for, and column C the upstream water body that is contributing. In this case, this is a particular lake. We don't have in this model information on diffuse sectors from upstream land water bodies, but that is possible to be enabled if you select so in Create SIMCAT. Now the information, as you can see, is not generated at a monthly level, it's generated at an annual level. And it's this one here, right, for livestock. So with some rounding, that will be 0.69, which is the value that we have seen in this particular table. Actually, it's not rounded, 0.0685. What I would like to explain at this part of the video is just try to give you an idea of what SIMCAT is doing behind the scenes. So the SIM nodes, if you can see here, this is the first reach because it's represented with the SIM node 1 and then 2, 3, and 4. They show you the order in which SIMCAT is processing the model. So it will start with this reach, it will start from the headwater, and it will begin modeling, so doing Monte Carlo, as we've seen, at each particular point in the river, every kilometer or wherever there is a feature, if that is before the next kilometer. And then it will keep track of all of the input loads, in particular when there is a discharge, but it can also do the same thing for diffuse sources if prompted to. Once it arrives to a confluence, for example, it will jump back to the next reach that needs to be processed, and it will hold all the tracking information in place until river 2 is processed, then 3, then it will process the confluence, then 4, and then it will again process the confluence between 1 and 4 and continue. So all of this information that is being tracked will be written to the GIS1 file and the D files, as we've seen before, and also to other specific files for a different set of outputs. We haven't seen in the videos every single type of output that SIMCAT creates because it does create many, and SAGIS only uses a fraction of them. But this tracking functionality is really powerful, and it allows you to apportion sources from all the different sectors all over the model in a very systematic and fast manner. A very famous quote used in modeling is by George E.P. Box: "All models are wrong, but some are useful." Every model is a simplification of reality, and because it is a simplification, it is also wrong. However, that doesn't mean that we cannot use them for decision making or for gaining a better understanding of what's happening in the real world. However, we need to take into account the uncertainty that these simplifications and assumptions produce. We like to distinguish between two different types of uncertainty: extrinsic and intrinsic uncertainty. Extrinsic uncertainty generally can be measured. For example, the confidence interval range around measured or predicted mean concentration values. In SIMCAT, however, sometimes we're forced to use default values. If we're using default values, it might be more difficult to measure the uncertainty around that particular parameter. Now, intrinsic uncertainty cannot be directly quantified, but we know it exists. This is the uncertainty that comes from the actual methods that the model uses to represent reality. So, for example, a key uncertainty in SIMCAT is that some sources of pollution are not taken into account. For example, small sources may be missed by mistake if they do not appear in the model. River ridge structure, and in general simplifications that we have seen throughout this video that we make to represent, for example, the river purification processes via a simple decay equation. But let's step back a little bit from all the detail of the modeling, and let's take a look at what SIMCAT does to help you understand that uncertainty. If we take a look at any plot outputs feature class, and we simply click on one output in the model, we get a stream of data corresponding to that particular record. So amongst many of SIMCAT outputs, the model already tries to give you the necessary information for you to take into account uncertainty and make better decisions. What I mean by this is that, for example, apart from the mean concentration, it's giving you the lower confidence limit and upper confidence limits for that mean concentration. It also calculates a series of statistical moments, like the 90th percentile and 95th percentile, and provides lower and upper confidence limits for those particular percentiles, as well as the 99th percentile. It also calculates similar confidence intervals for the load calculations that it does alongside the river reaches, and it also calculates the probability of compliance automatically. For example, in this case, it's telling us that this river ridge for this particular layer, which belongs to orthophosphate, and the targets that we have passed to this particular model, we can expect that a threshold of high for the water framework directive will be achieved almost 98% of the time, and perhaps good will be achieved slightly over 2% of the time. There's still a remnant. It could be that it's moderate, but it's not going to be poor or bad.
We've reached the end of the video, and also the end of this series of SAGIS training videos. On behalf of Atkins Realis and Ukwir, we sincerely hope that these videos will help you learn more about SAGIS and also in your daily work. Do consider subscribing so you get automatically notified if and when we publish more videos. Thank you very much for watching, and as always, happy modeling!